Welcome to the fascinating world of thermochemistry. Every chemical reaction involves energy changes. Some reactions release energy to their surroundings, making things hotter. These are exothermic reactions. Others absorb energy, cooling their surroundings. These are endothermic reactions. Understanding the difference is fundamental to chemistry, from the combustion that fuels our cars to the photosynthesis that powers our planet. In this presentation, we will explore the energy landscape of chemical reactions, learn how to read reaction energy diagrams, understand bond energies, calculate enthalpy changes, and apply these concepts through quizzes and worked problems. By the end, you will be able to predict whether any reaction is endothermic or exothermic just by understanding its chemical bonds. Energy diagrams are the visual language of thermochemistry. An exothermic reaction starts with high-energy reactants and ends with lower-energy products. The excess energy is released to the surroundings. The enthalpy change delta H is negative. In an endothermic reaction, reactants are lower in energy than products. Energy must be absorbed from the surroundings to make the reaction proceed, giving a positive delta H value. In both cases, the activation energy barrier E sub A represents the minimum energy required to initiate the reaction. Catalysts lower this barrier without changing the overall energy difference. The diagram on the right illustrates both profiles side by side. Notice how the exothermic pathway releases energy while the endothermic pathway requires energy input. At the molecular level, the energy change in a reaction comes from bonds. Breaking chemical bonds requires energy. This is always an endothermic process. You must put energy in to overcome the attractive forces holding atoms together. Forming new chemical bonds releases energy. This is always an exothermic process. Whether the overall reaction is endothermic or exothermic depends on the balance. If the energy released in bond formation exceeds the energy consumed in bond breaking, the reaction is exothermic overall. If bond breaking requires more energy than bond formation releases, the reaction is endothermic. For example, in the combustion of methane, we break carbon-hydrogen and oxygen double bonds, absorbing energy, and form carbon-oxygen double bonds and oxygen-hydrogen bonds, releasing more energy. The result is a net exothermic reaction. Exothermic reactions are all around us. Combustion of wood, gas, or gasoline releases heat and light. Hand warmers use the exothermic oxidation of iron. The reaction of strong acids with bases releases significant heat. Cellular respiration, the process that powers our bodies, is exothermic overall. Endothermic reactions are equally important. Photosynthesis absorbs sunlight to convert carbon dioxide and water into glucose. Melting ice, evaporating water, and cooking an egg all require heat input. Instant cold packs used for sports injuries rely on the endothermic dissolution of ammonium nitrate in water, which rapidly drops the temperature. Thermal decomposition reactions, like heating calcium carbonate to produce lime, are also endothermic. Recognizing these reactions in everyday life builds intuition for energy changes. Enthalpy change delta H is the heat exchanged at constant pressure. We can calculate delta H using bond energies, standard enthalpies of formation, or calorimetry. Using bond energies, we sum all bond energies broken, which is positive and endothermic, and subtract all bond energies formed, which is negative and exothermic. Standard enthalpy of formation delta H F naught is the enthalpy change when 1 mole of a compound forms from its elements. Hess's law states that enthalpy change is pathway independent. We can add reaction steps algebraically. Calorimetry directly measures heat by monitoring temperature changes in an insulated container. The equation Q equals mc delta T gives the heat absorbed or released. A positive Q means the system gained heat, endothermic, while a negative Q means the system lost heat, exothermic. Activation energy, E sub A, is the minimum energy that colliding molecules must have for a reaction to occur. Even highly exothermic reactions like the combustion of gasoline require an initial energy input, a spark, to overcome the activation barrier. This prevents spontaneous combustion. The Arrhenius equation relates the rate constant K to the activation energy. A higher E sub A means a slower reaction, since fewer molecules have sufficient energy. Catalysts provide an alternative pathway with a lower activation energy, speeding up the reaction without being consumed. Enzymes are biological catalysts that lower E sub A for biochemical reactions. In energy diagrams, the activation energy is the height of the energy hill between reactants and products. Let us bring everything together in a clear comparison. Exothermic reactions release energy to the surroundings, have negative delta H, and often feel warm or hot. Endothermic reactions absorb energy, have positive delta H, and feel cold. Combustion, neutralisation, respiration, and hand warmers are exothermic. Photosynthesis, melting, evaporation, and thermal decomposition are endothermic. In both cases, activation energy must be overcome. The total energy change in any system plus its surroundings is conserved according to the first law of thermodynamics. The universe overall tends toward lower energy states. This is why exothermic reactions are often spontaneous at room temperature, while endothermic reactions require continuous energy input to proceed. Quiz question 1. Which statement correctly describes an exothermic reaction? Option A, it absorbs heat from the surroundings. Option B, it releases heat to the surroundings. Option C, it has a positive delta H. Option D, it requires constant energy input. The correct answer is B. An exothermic reaction releases energy to its surroundings, typically as heat or light. The enthalpy change delta H is negative because the products have lower energy than the reactants. Quiz question 2. Photosynthesis is considered an endothermic reaction because Option A, it produces oxygen gas. Option B, it occurs in plants. Option C, it absorbs sunlight energy. Option D, it releases carbon dioxide. The correct answer is C. Photosynthesis requires energy input from sunlight to proceed. The products, glucose and oxygen, have higher chemical energy than the reactants, carbon dioxide and water, making delta H positive. Quiz question 3. Bond breaking is always a blank process, and bond formation is always a blank process. Option A, endothermic, endothermic. Option B, exothermic, endothermic. Option D, endothermic, exothermic. Option D, exothermic, exothermic. The correct answer is C. Breaking bonds requires energy input, endothermic, because attractive forces between atoms must be overcome. Forming bonds releases energy, exothermic, as atoms settle into lower energy bonded states. Quiz question 4. What does a catalyst do in a chemical reaction? Option A, it increases delta H. Option B, it decreases the activation energy. Option C, it makes endothermic reactions exothermic. Option D, it is consumed in the reaction. The correct answer is B. A catalyst provides an alternative reaction pathway with a lower activation energy. This increases the reaction rate without being consumed. Catalysts do not change delta H or the thermodynamics. Quiz question 5. For the reaction N2 plus 3H2 gives 2NH3, delta H equals negative 92 kilojoules. This tells us the reaction is option A, endothermic with energy absorbed. Option B, exothermic with energy released. Option C, neither, delta H is 0. Option D, impossible to determine. The correct answer is B. A negative delta H of negative 92 kilojoules means the reaction is exothermic. Energy is released to the surroundings. The ammonia product has lower enthalpy than the reactants. Problem 1. Bond energy calculation. Calculate delta H for the combustion of methane using bond energies. Methane plus 2O2 gives CO2 plus 2H2O. Bond energies in kilojoules per mole. CH is 413, O double bond O is 495, C double bond O is 799, OH is 463. Step 1. Identify all bonds broken in reactants. Methane has 4 CH bonds, each 413 kilojoules per mole. O2 has 1 double bond per molecule, 2 molecules. Total O double bond O is 990. Sum of bonds broken equals 4 times 413 plus 2 times 495, which is 2,642 kilojoules per mole. Step 2. Identify all bonds formed in products. CO2 has 2 C double bond O bonds, each 799, total 1598. Water has 2 OH bonds per molecule, 4 total, each 463, total 1852. Sum of bonds formed equals 3,450 kilojoules per mole. Step 3. Delta H equals sum broken minus sum formed. 2,642 minus 3,450 equals negative 808 kilojoules per mole. The negative sign means the reaction is exothermic. Problem 2. Calorimetry. A 50-gram sample of water at 22 degrees Celsius absorbs 628 joules of heat. What is the final temperature? The specific heat capacity of water is 4.18 joules per gram per degree Celsius. Step 1. Use the calorimetry formula Q equals mc delta T. Step 2. Solve for delta T. Delta T equals Q divided by M times C. Plugging in 628 divided by 50 times 4.18. Step 3. Calculate. 50 times 4.18 equals 209. 628 divided by 209 equals 3.0 degrees Celsius. Step 4. Find final temperature. T final equals T initial plus delta T. 22 plus 3 equals 25 degrees Celsius. Since Q is positive, this is endothermic, the water absorbed heat. Problem 3. Enthalpy of formation. Calculate delta H naught for 2CO plus O2 gives 2CO2. Given delta H F naught of CO is negative 110.5 kilojoules per mole and of CO2 is negative 393.5 kilojoules per mole. Step 1. Apply the enthalpy of formation formula. Delta H naught equals sum of delta H F naught of products minus sum of delta H F naught of reactants. Step 2. Calculate products sum. 2 moles of CO2 times negative 393.5 equals negative 787 kilojoules. Step 3. Calculate reactants sum. 2 moles of county times negative 110.5 equals negative 221. O2 is an element in its standard state. Delta H F naught is 0. Total is negative 221. Step 4. Delta H naught equals negative 787 minus negative 221. Negative 787 plus 221 equals negative 566 kilojoules. The reaction is exothermic. Problem 4. Endothermic or exothermic. When 0.5 grams of magnesium reacts with excess HCl in a calorimeter, the temperature of 100 grams of water rises from 20 degrees to 45 degrees Celsius. Is the reaction endothermic or exothermic? Calculate Q. Step 1. The temperature increased from 20 to 45 degrees Celsius. Delta T equals 25 degrees. Temperature rise means heat was released. The reaction is exothermic. Step 2. Calculate heat absorbed by water. Q water equals mc delta T. 100 times 4.18 times 25. That is 10,450 joules or 10.45 kilojoules. Step 3. The reaction released this heat. Q reaction equals negative Q water, negative 10,450 joules. The negative sign indicates heat flowed out of the system. The reaction is exothermic. Problem 5. Hess's law. Calculate delta H for C plus 1/2 O2 gives CO using Hess's law. Given equation 1, C plus O2 gives CO2, delta H1 equals negative 393.5 kilojoules. Equation 2, CO plus 1/2 O2 gives CO2, delta H2 equals negative 283 kilojoules. Step 1. Identify the target reaction. C plus 1/2 O2 gives COF.